Hi, I'm teacher Melai, and let's talk about basic definitions and notation. So this is actually part of the lesson number 1, which has the following learning objectives. So the first one is to review the terminologies, notations, and the basic properties of sets, and to serve as a starting point for the development of the ability to discover and prove mathematical theorems. For the outline of the whole chapter, which is entitled Set, so we are going to discuss the following topics. So the basic definitions and notation, set operations, algebra of sets, Venn diagrams, counting properties of finite sets. So here, our focus is the first one, which is the basic definitions and notation. So, but before we start, let us also consider the man behind sets. So we have here the picture of George Cantor. So the real name, or rather the full name of George Cantor is George Ferdinand Ludwig Philipp Cantor. So he was born in March 3, 1845 at St. Petersburg, Russia, and died January 6, 1918 in Halle, Germany. So he is a German mathematician who founded the set theory and introduced the mathematical meaningful concept of transfinite numbers, and definitely large but distinct from another. So this information is obtained in Britannica.com. Okay, now, what is a set? So a set may be thought of as a well-defined collection of objects, and it is denoted by a capital letter. So we use capital letter A, B, X, Y, and others. And the elements, or the objects rather, the objects in the set are called the elements. And we use lowercase or not capital letters, so such as for small letter A, B, X, Y, and others. So we also have an expression that looks like letter E. It's actually a Greek letter, which means, so I am referring to this one, letter epsilon, Greek letter epsilon. And it represents the statement that, so this statement, small letter A, epsilon, capital letter A, means that the object A is an element of set A. While if we place a slash, so epsilon with a slash, it means that it is not an element. So I am again referring to this one. So this means that it is that object X is not an element of set X. Okay, so next. So let us also consider the next slide. Okay, let's go back. So here, we will also be talking about the methods of describing sets. So as mentioned, we use capital letters to denote A. So in writing now all the elements or objects of set A, for example, what we use is the curly bracket. So it is enclosed with open and closed curly bracket. And inside it, it contains the element. So for example, we can present our set using roster method, and the other one is set builder notation. So in our discussion here, in the upper part of our slide, it is the roster method or the listing method. So we use capital letter A is equal to, and then the curly bracket now. So we have, for instance, countries like Philippines, Malaysia, China, Japan, or set B contains the elements 2, 4, 6, 8, and 10. So what we also have to consider the important facts in using roster method. So in using this, the order of the elements are not relevant. So we can actually disarrange this, especially if this contains exactly number 2, 4, 6, 8, 10 elements only, or it is. Later we are going to also to introduce the word finite. So it's a finite set. It contains a fixed number of elements. So the elements can be listed. So even if, for example, we have elements, or we can introduce a set that contains 2 and 2 and 3 and 4, this is actually the same with 2, 3, and 4. So the element should be listed once. But of course, this is the correct 1, 2, 3, and 4 only. While for the second method of describing set, we have the set builder notation. So this is known as a rule, description, or method. So like for instance, set A is equal to, so let me just read this as is. So we have here a curly bracket that enclosed our rule, and the element x slash and then x, and it contains now it satisfies some property or properties. So it's the rule. It talks about the rule. So for example, if we're going to present it this way, this means that a set A is the set of all objects X such that X satisfies some property. So if we will consider letter B, set B is equal to, this is read as set of all objects X such that X is a natural number less than 50. Or we also have another example. Set C is the set of all object X such that X is the town in Nueva Vizcaya. Okay, so if we're going to compare roster method compared with set builder notation, for roster method, it's quite easy to use. However, if there is no definite rule, like for example, it is infinite, but there's no rule, it could be hardly be written like the given examples here. So for instance, for our country, A is equal to Philippines, Malaysia, China, Japan, we cannot just simply place dot, 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 or ellipsis that represents other countries, especially if the properties or the method or the rule is not clear. Unlike for set builder notation, we can definitely identify or say that it belongs to the, what do you call it? If it belongs or if it does not belong to the given set. Okay, so what is a finite set? So this are the important types of set. So it's countable and all the elements can be listed. So just like the given example for our roster method or the listing method. For infinite set, it is impossible to list all elements. So if we're going back to the given example here, for element A, or rather set A, so it is a finite set. It's very clear that the elements are Philippines, Malaysia, China, Japan. So we have 4 elements. And also for letter set B, 2, 4, 6, 8, 10. It is countable. We have 2, 4, 5 elements. And also with example for set builder notation, it is a natural number less than 50. So we know what are the natural numbers less than 50. And so we can identify, we can list it. And then for letter C, we also know what are the towns of or rather the towns in Nueva Vizcaya. So the given examples here are all finite set. While for infinite set, it is impossible to list all elements. So just like, for example, if we set it that set A is set of all real numbers, so it's difficult to write all the real numbers because it's infinite. So it is considered infinite set. While for the next one, we have the universal set. It contains set containing all objects. Okay, so we also have here some definitions. So as mentioned in our descriptions or definition that we can use capital letters. Here we have a fixed letter for the following numbers. And like for instance, for N, this is the fixed letter that we use for positive integers or natural numbers. And then for Z, it refers to all integers. Letter Q is rational numbers. Letter R represent real numbers. Letter C represent complex numbers. So we cannot, of course, interchange the letters, and we cannot use any other letters aside from the given. So this is based on the definition. So we are assigning capital letters for these numbers. Or sometimes it is also written as, instead of bold letter N, in other books, we have double line for the first letter here, and then N, and then Z. Just to, again, also to emphasize as is, it is bold. Okay, next. For our definition number 2, a set I, all of this whose elements or real number is called an interval if and only if whenever A and B are elements of I and C is a real number between A and B. So C is in between A and B, so C is element of I. Okay, so for our definition number 3, so just to elaborate this interval, so we actually have 9 types of intervals as described by the following terminology and definition, in which A and B denote a real numbers. So we have X, element of a real number, and from this is X greater than or equal to A but less than or equal to B. As of course, this can be written as square bracket A. It's an open square bracket A and close square bracket B. So if we have the notation equal sign, we use the square bracket. So it is a closed and bounded interval because it contains A and B. While for number 2, if you notice, we remove the equal sign. So it means that A and B are not included. So we're going to use open and close parentheses for A and B. So it is an open and bounded interval. It's not closed because it does not contain the equal sign. So we have open parenthesis A, comma, and B, and then closed parentheses. So for number 3, so it is closed open because it is greater than or equal to A, but it is only less than B. So it's one-sided. So it's a open bracket for A, but it's a closed bracket for A, but an open bracket for B. So we use a square and a round bracket. For number 4, so similar with number 3, except that we interchange or the equal sign is moved to our X less than or equal to B. So for number 5, we use that, we rather define it as open and closed. So for the number 3, it is closed open. For number 4, it is open closed bounded interval. So again, we use the symbol, interval symbol for open and close as round bracket and then and close with a square bracket. For number 5, A is less than or equal to X. So it is a closed and unbounded above interval. So it means that, so we have X is greater than or equal to A. So all other values now are greater than A. So we have a closed bracket for A, and then we use the sign infinity and then open a closed parenthesis. So the round bracket. So with this, we have the open and closed parentheses, which also use the round bracket. For number 7, so for letter B, we have also closed and opened below interval, open and unbounded below interval. So if you notice now, as mentioned, we are using the word close if it contains the equal sign or that letter or number it represents is included. While if it is not included, we say that it is open. And then for number 9, R itself is an interval and it is sometimes denoted with from negative infinity to positive infinity. It is, of course, open and unbounded below and above interval. Okay, so let's have here an example. So assuming that the universal set is R, so it's a real number, solve for the following inequalities and express each solution set in an interval notation. So to do this, so let's take note of the value 8x minus 10x less than or equal. So let us consider where is it now? So let's consider new share. Let's use a whiteboard. Okay, so we have the following value, 8x. So let us just go back to that, minus 10, and then we have 16. So this is the number. So how are we going to solve for this? So we are going to solve for the value of x. So what will we do? So we have 8x minus 10 less than or equal to 16. So to remove 10 by addition property of inequality, so if we're going to add 10 to both sides, okay, so negative 10 plus 10 is 0. So what is left is 8x less than or equal to 26. Now, to remove 8, we are going to multiply both sides by 1/8 by multiplication property. This is multiplied by 1/8 because 8 over 8 is x. So x less than or equal to 26 over 8. So we can still reduce this. And to reduce this, this is x less than or equal to 26 over 8 is 13 over 4. So x is less than or equal to 13 over 4. So it is less than, which means it is a lower number. So we have the interval notation, 13 over 4, we have the equal sign. So we are going to use the square bracket, comma. It is unbounded. So we have here negative infinity and our, what do you call this, round bracket. So this is our interval notation. So x is less than or equal to 13 over 4. So it is a bounded. It's bounded in 13 over 4, but it is unbounded after the lesser number after that. It's negative 8 comma 13 over 4. Again, we are going to emphasize this is the round bracket and then the square bracket here because it contains 13 over 4. Okay, so let us see. So what's next? So aside from that, we also have here some properties like equality. So if A is equal to B, it means that if every element of A is also in B and vice versa. So all elements also, or every elements also in B is also in A. So just like, for example, if set A contains 1, 2, 3, 4, then set B also contains 1, 2, 3, 4. Set A is equal to set B. For reflexive, A is, of course, equal to itself. So A is equal to A. For symmetric, so in case, so as mentioned in our given example, 1, 2, 3, 4, if A is equal to 1, 2, 3, 4, and B is equal to 1, 2, 3, 4, symmetric property, A is equal to B, then B is also equal to A. If we add one more set, set C, and set C now also contains elements 1, 2, 3, 4, then A is equal to B, B is equal to C, then A is also equal to C, and that is the transitive property. Okay, so other more terminologies that we need to consider in our discussions or the following. So we have the subset, we have the notation. So this is the notation for subset. So it means that every element of A is also an element of B. Superset, so it means that B is a superset of A. We also have the proper subset. So if you notice, we just remove the bar below and then power set. And other than that, we also have the terminologies like intersections and union. So here, we're not going to discuss this in detail because there is a separate video for this. Okay, so this ends the discussion for the basic notation. Thank you very much for watching.